Hi, everybody. So, as you've probably seen, we had to change around the schedule a bit because of all the cancellations. So this is kind of a mini catch-up week. There's really just this one new thing to do, um, along with the usual stuff. And then next week there will be a whole new unit, which will be our last new stuff before Thanksgiving. And hopefully by then we'll have a chance to we'll have finished the biodiesel project, the analysis. And so we can finish that project and go on from there. So this week we're going to be looking at the mole concept, and this came up a little bit when we talked about chemical equations, but I want to give you a little bit more background about it. So first, what is a mole? Well, you may have heard this word as it applies to or in the context of chemistry at some point in the past, and it may have confused you or whatever. But the important thing about the mole is it's just a word for a number. And we have other words in our language for numbers. For example, a dozen is 12, a score is 20. I'm not sure this one's correct. I think that's made up for this, but another one would be like a pair. A pair is two. So it's just a word that means a number. And for a mole, that word means a very, very large number, which is this one right here, 6.022 times 10 to the 23rd. So if we were to write that entire number out, that would be something like, um, let's see, 1, 2, 3, 4. All right, so that's the actual number written out. If you're not really familiar with scientific notation, it's a really big number. And I think that's what kind of throws people off sometimes. Oops, there should be another 2 here also. Is that it's such a big number, it's hard for us to think about what that really means compared to these other numbers that we can grasp. But the reason that we need such a large number in chemistry and why it has this special name and all of that is that it brings us, it joins two important domains. One is the domain of the atoms and molecules, so these super, super tiny particles. These things are so small that we can't really manipulate or count them without extremely specialized instrumentation. So we want to be able to manipulate and count these tiny, tiny particles at a scale that we can manage with our own laboratory instruments. And so, as it turns out, if you take about this many of an atom, you've got something that can be weighed on your typical balance in the lab. So, to, I don't think it says it in here. Well, yes, it does. So, we'll get to that in a second. So let's look at this document. We'll go through some of these together, and then I'll leave some of them for you to finish up. But I think you'll get the idea. It's not that difficult. All right. So one elephant has one trunk and four legs. Okay. And one methane molecule contains one carbon atom and four hydrogen atoms. So the point of these two definitions is this is something that is obvious and we know about, and this is maybe something that is less obvious, but we can think about how those are similar. All right, so let's answer some of these questions together. How many trunks are found in 1 dozen elephants? Well, a dozen is 12, and there's one trunk per elephant, so it must be 12 trunks, right? And how many legs are found in 1 dozen elephants? Well, you've got 1 dozen times 4 legs per elephant times, whoops, 12. I spelled that wrong. All right, you know what I'm writing here. Elephants. 12 elephants per dozen. 48 legs, right? So we know how many elephants are in a dozen, and we know how many legs are in an elephant. So we just multiply that, and then we've got how many legs are in a dozen elephants. All right. So now we can start increasing our numbers, right? How many trunks are found in a score of elephants? Well, If a score is 20, then one trunk per elephant, 20 trunks. How many legs are found in a myriad elephant? So let's say a myriad is 10,000. 10,000 elephants. How many trunks would you? Oh, yeah. How many legs would you find in 10,000 elephants? Well, there's 4 legs per elephant, so that would be 40,000. All right, see where I'm going with this? So the point of this and dealing with this elephants and legs and dozens and scores is that when we move up to atoms and moles, it's not going to be any different. So how many carbon atoms are found in 1 dozen methane molecules? That's really just like asking how many trunks are found in 1 dozen elephants, because there's 1 carbon atom per methane molecule. We found that up here. 1 carbon atom per methane molecule. So if we have a dozen 12 methane molecules, we must have 12 carbon atoms. The hydrogens then in methane are kind of like the legs on the elephant. There's 4 per molecule. So if we have 10,000 methane molecules, we must have 40,000 hydrogen atoms. So the point of all of this, again, is moles are a way of counting. And in that, they're a very large number. So when we say how many elephants are in 1 mole of elephants, well, it's a lot of elephants. It's an unimaginably large number that's essentially devoid of any meaning because it's just so big. You can't have that many elephants. You can't. That's not meaningful. But it's still just a way of counting things, and we can still deal with that. So, like, let's look at now what becomes a little bit more complicated of a question. How many trunks are found in 1/2 mole of elephants? So we need to know a couple things here. We know there's 1 trunk per elephant. And we know that there are a lot of elephants, 6.022 times 10^23 elephants per mole. So we need to take half of that number to find the number of trunks in a 1/2 mole of elephants. But think about what that means. So I could put this into my calculator and I'd get that 3.011 times 10^23 is half of this, right? So the answer becomes 3.011 times 10^23 trunks in a 1/2 mole of elephants. All right. But this big number, again, it's so big, it's kind of clumsy. It can be hard to deal with. If you don't have a good calculator, it can be really difficult for calculations. So it's a lot easier if we can just say 1/2 a mole. That's another way of counting. Instead of saying I need 3.011 times 10^23 trunks, I can just say I need 1/2 a mole of trunks. 1/2 mole of trunks. And so it's the same as we go on with the atoms, and you can apply these in the same way. It's a lot of the same numbers over and over and over again. But the point is that the mole allows us to count very small things in batches so that we don't have to think about them individually. All right. So now let's talk about how we do that, how that would actually work. In order to count those things in those batches, we need to be able to convert between counting, which we can't do because they're too small and there's too many of them, and weighing, which is what we ultimately want to do. That's what we can do. And this is actually where that big number comes from. It's the number that allows this to work. The mass of 1 mole of any pure substance is equal to the average atomic mass expressed in grams of that substance. For example, the average atomic mass of a helium atom is 4.003 atomic mass units. So that's the average mass of a helium atom. And then if you took a mole of helium atoms, all you have to do is change that unit from AMUs to grams. So 4.033 grams of helium gives you 1 mole of helium. And where do you find those average atomic masses? You find them on the periodic table. So if we look at the periodic table back here, all these little numbers underneath the atoms, like you can see a helium up there, those are the average atomic masses. And so if we want to know how much a mole of any given element weighs, we simply look at the atomic mass. So that number, the reason that number doesn't have any units on the periodic table is it has two different possible units. It can be that number in AMUs, which gives us the weight of the atom in atomic mass units, or it can be the weight of a mole of that atom in grams. All right, so if we think about that a little bit and how we can use that, is we now have a way of weighing things and then counting them. And the reason that's so important, if you remember back to the chemical reactions and equations worksheet, when we talked about those, we had these coefficients in front of the substances and in front of the species, and it turns out that those coefficients are how we set up the reaction, because we know that we need two hydrogen molecules to react with one oxygen molecule to make water. So they need to be in this 2-to-1 ratio. And that ratio is a counting ratio. We have to have twice as many hydrogen molecules as oxygen molecules. And this is how we count them, is we figure out how much 2 moles of hydrogen atoms would weigh, or hydrogen molecules would weigh, and how much a mole of oxygen molecules would weigh, and then we can put those together in that particular ratio. All right. So let's look at an example of how that would work. We're going to look at this problem here. If you measure out 69.236 grams of lead, how many atoms of lead do you have? Make a unit plan first. Show work. So how do we figure out the number? And like this kind of stuff, like I said, this comes from a textbook where it's in with a lot of other stuff, but you can solve the problem however you want. All right, so we want to know how that's a reasonable amount of lead. We can measure that out. And we want to know how many atoms of lead does that correspond to, or how many moles of lead does that correspond to. So we need to start with that number, 69.236 grams. And then we're going to multiply it by a number that relates moles and grams. So we want to know in 1 mole of lead, how many grams would that be? And to find out how many grams that would be, we're going to look it up on the periodic table. That's that average atomic mass. So I'll pull this up. It's right by my shoulder here. It is 207.2, I think. It's really small on my screen. Sorry. Sorry if that's wrong, but I'm going to say 207.2. Right, and let's do that first. So that's going to give us, pull out my calculator here. By doing that division, we get 0.334 moles of lead. By the way, the abbreviation there for mole, you can see, is just MOL. Not a great abbreviation, but M is meters, MO is months, so that's as short as we can get, unfortunately. All right, so we've got that many moles of lead. That's a count now. That's telling us that's going from a weight to a count by dividing by that, what we call the molar mass. And so now if we want to take that final step to how many atoms of lead do we have, we would multiply that. Give myself a little more space here. Oh, sorry, I didn't realize I didn't go back to the screen here. Take off my periodic table. Okay, so 207.2 grams of lead goes here. So we divide by that average atomic mass, which is grams per 1 mole. And that leaves us with the number of moles, which again is a count. So then, from there, we can multiply that times that big number called Avogadro's number to get our total number of atoms. And so now we've gone from weighing, which we can do in the lab, to counting, which is what we need for the equation. So if we were to take a sample of lead and weigh out 69.236 grams of it in the lab, right, grams of lead, then by doing a little calculation, we can also know exactly how many of those atoms we have, and that's important for doing the chemical reactions. All right. The other thing you can do is you can find the mass per mole, or the grams per mole, so how much would 1 mole weigh, of larger molecules by adding up all of the constituent parts. So if we look at this molecule ethanol here, we can see it has 2 carbon atoms, 6 hydrogen atoms, and an oxygen atom. So 2, 6, 1, right? So we can look up those weights on the periodic table and then add them together. So I've got 2 carbon atoms times about 12 grams per mole per carbon. There's some decimal places there. We're just going to leave it like that. And then we're going to add that to the numbers for hydrogen and then for oxygen. So we've got 2 times 12 is 24, plus 6 is 30, plus 16 is 46. So that 46 number, remember, means 2 things. The average mass of one individual molecule of ethanol is going to be 46 atomic mass units. The mass of 1 mole of ethanol is that same 46, but this time it's grams. So we can weigh out 46 grams of ethanol and know that we have about a mole. And so if we have less than that, if we have 0.5623 moles, then we're going to have a portion of that weight, right? And so you can multiply that by the moles by the grams per mole to get the mass of a given number of moles. Okay. So you can work on some of these other ones. Let me know if you have some issues. What I really want to go to now is this end part. I'm on upcoming quizzes and such. I'm not going to ask you to specifically calculate particular amounts of moles and molecules and stuff. I think that's a little beyond what we need to do in this class. What I want you to be able to do is answer questions like these here, where we take a number of or we think about what it means to count in moles versus weighing in grams. So let's go through a couple of these together. So first one, 1 mole of NH3, that's ammonia, weighs more than 1 mole of water. Is it true or false, and why? So in this case, how would we figure that out? Remember, 1 mole is a given amount. It's like a batch size. So if we have that many of one versus that many of the other, we have equal numbers of both. So we're saying we have equal numbers of ammonia and water. So how are we going to figure out which weighs more? We're going to figure out which weighs more by the one that has more grams per mole. So we're going to add up these weights in each case and decide which one would, a mole of which one would weigh more. So NH3 would be 14 plus 3, because I know these masses. You can look them up on the periodic table. That's 17 grams per mole. And then water would be 16 for oxygen plus 2 for each hydrogen, or 2 times 1 for each hydrogen. And so that's 18 grams per mole. So if we have 1 mole of each, the one that weighs 18 grams per mole is going to weigh more than the one that weighs 17 grams per mole. And so we can say then that this is false, that 1 mole of water will weigh more than 1 mole of ammonia. Okay, let's look at the next one. There are more carbon atoms in 48 grams of CO2 than in 12 grams of diamond, a form of pure carbon. So 48 grams of CO2 that's obviously a bigger number, but that doesn't necessarily mean there's more carbon, because there's also a bunch of oxygen there. So we have to figure out how much carbon is actually in there, how many carbon atoms are in there, versus how many atoms are in the 12 grams here that's totally carbon. So to do that, we convert from grams to moles. So instead of having weights, we have counts. So 12 grams of diamond, since carbon is 12 grams per mole, that's about, or just a little over that, we're going to say that's about 1 mole of carbon. And I'll show you that on the periodic table here. So carbon is where? Okay, right up here, 12.011. So if we had 12 grams of that, we'd have just under a mole of carbon. All right, let's look at CO2 then. So for CO2, we've got carbon and 2 hydrogens. If we add those together, that's 12 plus 16 for oxygen times, there's 2 of those there. So that's 32 plus 12 is 44. So carbon dioxide is 44 grams in a mole. And if we have 48 grams of CO2, that's a little more than a mole, right? So just over 1 mole. And since there's 1 carbon atom per molecule of CO2, if we have a little bit over a mole of CO2, we also have a little bit over a mole of carbon atoms. So a little bit under a mole and a little bit over a mole. So that means there's going to be more carbon atoms here. All right, I'll save C for you. Try that out. And then let's look at D and E together. So D, this is where it gets a little confusing, and we really have to try to keep it straight what's being talked about here. D says the number of copper atoms in 100 grams of copper is the same as the number of copper atoms in 100 grams of copper 2 oxide. So you have the same weight of each of these. Do you also have the same number of copper atoms? And the answer here is no, you don't. The reason is some of that mass in the copper 2 oxide, some of that mass is taken up by oxygen. So the amount that's taken up by oxygen is not copper, and therefore there is less copper in this sample, in the second one, than in the first one. So this is false. There's more copper in the first sample here that is pure copper than in the second that is copper and oxygen. Okay? So hopefully that makes sense. Now let's look at a very similar sounding question, but with actually a different answer. E, the number of nickel atoms in 100 moles of nickel is the same as the number of nickel atoms in 100 moles of nickel 2 chloride, NiCl2. When you first look at this, it looks really similar to part D, right? We had 100 and 100, and then this one was pure, and this one had some other stuff here. But look at the difference. Now, instead of grams, we're talking about moles. And moles is a lot different because now we're counting. And if that word moles throws you off, think about dozen or just one. Think about counting individual pieces. If there were 100 pieces of nickel versus 100 pieces of nickel 2 chloride, well, look at nickel 2 chloride. In that, there's 2 chlorides for every 1 nickel. So each piece, let's say, whatever a piece is, each piece of nickel 2 chloride has 1 nickel in it. So if we've got a piece, we've got a nickel. If we got 2 pieces, we got 2 nickels. 3 pieces, 3 nickels. So in this case, they are actually the same because 100 moles, 100 pieces of nickel, 100 batches of this is the same as 100 batches of this, which will still have just 1 per piece. Right, so this one's false, this one's true, and then you can write y. So for the last one then, F, I'll let you try that one. There are more hydrogen atoms in 2 moles of NH3 than in 2 moles of CH4. So remember, I'm not going to grade these for very like you have to get them all right. I want you to try them, and I'm more interested in your justification. Like, can you actually think through this and figure out why you're picking one answer versus the other, not just guessing and trying to see if it's right. All right, so see if you can really justify it. These are the types of things that I want you to be able to do when it comes to moles, thinking about how to count in these batches. Don't worry too much about if you couldn't quite get these calculations up here. Definitely give them a try, but if they're a little beyond your math skills, that's okay. This is what I'm more interested in for our class. All right, so let me know if you have any questions as you go through this, and I will hopefully see you in lab this week and next week as we return to campus, I hope. So see you then. Bye.